Let us consider a simple UAV, a quadcopter model with 6 degrees of freedom. It wants to move from point A to point B to point C, whereas the line AB is perpendicular to the line BC. A simple quadcopter UAV with 6 degrees of freedom can easily move to point B and then yaw 90 degrees to point C by moving forward. And now let's consider a plane-like UAV, which is called as a fixed wing. These plane-like UAVs need to have a minimum bank angle in order to rotate itself. Now, if we force the UAV to move like the quadcopter one, it will need to rotate after getting into the point B. Now, let us consider another way to path the UAV. We could use an algorithm that considers the bank angle and also the heading. Now, it has 6 different paths it could take. Circle to circle to circle path, or it could take a circle, line, circle path. Now we could ensure that the UAV takes the most optimal path by finding the minimum distance it takes from point A to point B from all the iterations or the enumerations of path it could take. One of the problems in modeling UAV path using a Dobbin's algorithm is that the algorithm assumes that from point A to point B, there are no obstacles. The workaround is that we could use an algorithm that considers obstacles. One of those algorithms is an A-star algorithm. Now, we can model the obstacles, the set of obstacles, as a set of nodes it needs to visit, right? But the core problem coming from that A-star algorithm itself, it does not have the property of a bank angle in which we know that it can be modeled by a heading. Now, we have an algorithm called the hybrid A-star. So for the hybrid A-star search, we create a search space which can be represented as a 2D space, in which in that 2D space exists a certain amount of cells. Each cell exists or associates with a continuous state of x, y, and theta, and expands using the discrete motion primitives. This ensures that the output trajectory is kinematically feasible for a certain configuration of a plane, and then we guide the search using an admissible heuristic that takes the maximum of the obstacle-free Dobbin's distance and the 2D obstacle-aware distance. The final stage of the pipeline is that after we have a set of results, now we have to order the tour in which the plane should take. We do this by using an algorithm that is actually used in one of TSP solutions. We use the HealthCarp dynamic programming algorithm to solve the sequencing of targets given by the set of A-star search. There are 3 test cases that I did to test the pipeline against real-life cases and some theoretical cases. The first one is that I benchmarked the planner in an obstacle-free circular layout of 10 targets, which was also used to test the previous researches regarding Dobbin's path. And from the overlay from this picture, we know that hybrid A-star actually successfully converges to the continuous Dobbin's search. But at the same time, because the hybrid A-star primitive uses discretization, and the penalty is about 6.35%. This confirms that this planner converges to the theoretical baseline while at the same time highlights the trade-off of state space discretization. Lastly, I decided to test the algorithm and the waypoints generated from the previous test case using a gazebo flight simulator, which is close enough to the real-world physics model, and also uses an EURDF from the ArduPilot firmware, and also using a ROS2 and MAFLink protocol. Because there are some discrepancies from the algorithm I created due to certain assumptions, there are some adjustments that are needed to be done before moving on into the physical real-world simulation. Now, because in the simulation itself, the aircraft has mass, inertia, aerodynamic constraints, and also it does not necessarily move in a constant speed. There are accelerations during banking. We need to implement an inflation buffer in the path planner. This buffer itself guarantees that even when the physical plane cuts corners or drifts due to the wind, it remains a safe distance from the obstacles. From this image overlay, we can see that for all targets and the obstacles surrounding them, the planner successfully generated a set of waypoint that visits all target but at the same time does not collide with the obstacles surrounding